Hi, so my name's Aria, and today I'm going to talk to you about event discovery, content models, and relevance. So I'll briefly pictorially recap what Oren just said about my background. So I actually started life as a math major. I loved math so much I even got a tattoo. Um, and so my background is primarily in math. I actually did a little bit of quantitative finance stuff post undergrad, and then I did my PhD and postdoc in statistical natural language processing and machine learning. I don't have a parse tree tattoo yet. And then I kind of veered away from academia and went in and found a startup called Prismatic that as Oren said, is a personalized news reader. And then I now work in a small fruit company in Cupertino, California, that I can't say anything about. So today I want to talk about three different problems that I've worked on in the past. The first comes back from the tail end of my academia days, and it'll be about event discovery from social media feeds. This was worked on in 2010. Then I'll talk a little bit about content models for information extraction. Again, this is work I did kind of in my postdoc days as well that I never really got to go out there and expound on because I went to go do the startup. And finally, I'll talk a little bit about some of the relevance engineering at Prismatic. And this will focus less on the machine learning and more about the problems that happen when you actually productionize research. So first up, event discovery from social media feeds. So this is work done in collaboration with Ted Benson and Regina Barzilay while at MIT. So the problem that I was interested in at this time was automatically constructing events from Twitter. Right. So in particular, what I found interesting about Twitter as for natural language processing back in 2010 was the fact that discourse was distributed. Right. So throughout my graduate career, I was interested in larger than sentence kind of NLP, and Twitter, in some sense, was the most distributed discourse that there was. So the way that I went to think about this was if we take as input a stream of Twitter messages, which happen to be about concerts. So I'll give you guys a few seconds to read some of these tweets. So each of them is kind of hinting at some kind of concert event, and the output that we want to actually guess at is kind of a canonical database of the actual underlying events. So for this particular application, it would be who is the actual canonical artist and what is the venue. Right? So there's some sense in which this is a little bit different than the standard information extraction task. So the first is that messages are really short, right? And that's both a plus and a minus depending on what exactly you're trying to do. The second is that individual messages may not actually contain all of the fields of what you're doing. So one message might say, I'm really stoked to go see Radiohead, without saying where they're playing. Another message might say, stuck in the concert line at the Coliseum, without saying that they're going to go see Radiohead. So there's this notion in which kind of the information is distributed across messages. But the other nice thing is that they're really redundant because you get a lot of them, which is actually pretty useful. So the other is that messages are expressed in a colloquial language, right? So way too much NLP is over kind of newswire text, right? And so things become pretty difficult once you actually deal with the kind of text that users might enter. And so in particular in Twitter, you have all sorts of particular conventions like using a user mention as to refer to a person or a place, as well as constructions like this. Hashtags actually by themselves, just parsing hashtags for kind of structured information is kind of a task in and of itself. So we'll handle the former here, but not the latter. So this is kind of how I think this differs from standard information extraction. So I'm going to dive into the details of the model. There's an aspect of the model which looks like standard information extraction. You've got a message, tokens in that message which are always observed, and then individual labels on each token. As is common practice in kind of information extraction tasks, there's kind of a background labeled none, and then there's some labels of interest that you care about for extracting chunks. So in particular, artist and venue are the only two non-background fields. Next, there's another aspect of this, which is you want to cluster the actual messages according to the underlying event that they're discussing. So this departs a little bit from some of the more standard IE work. And lastly, you want to actually induce a canonical value for each field. So you have a bunch of messages. They're each textually referencing some underlying entity, and you want to pick a canonical version of that. And so here's an illustration of some more of that. So I'm going to use the letter R to refer to a canonical record. And I'm going to use the letter A to refer to these alignments between messages and canonical records. Okay? And M for messages. Okay, so here's the overview of how the model works. The sole source of supervision during training will actually be gold canonical records. When we train a model, we're not going to actually be told any token labels for individual messages, nor any alignments. So this fits broadly into distant supervision. So we don't see alignments, we don't see message fields during training. The only thing we basically see is more or less something we extracted from a website, which is canonical artist name, canonical venue, place, and the time. So we're going to take those three aspects, message level analysis of labeling individual tokens, message alignment or clustering, and then finally canonical event record compilation, so picking a canonical value for each field. So this is going to be learned as a factor graph model. So there's sequence labeling, which looks like a CRF. There's a term popularity factor, which is encoding how compatible is this message and its labels with the underlying canonical record. There's record uniqueness, which is encouraging finding records which are distinct from one another. So you don't want to find two Radiohead records, for instance, in the same night in the same place. And finally, record consistency, which is actually encouraging the model to try to find events where multiple fields are expressed in the same message. Because otherwise, there's no incentive. You can mix and match, right? So, Radiohead can play at one place, and some other band can play at some other place. And if there's no incentive to at least try to identify events that occur in the same event fields that occur in the same message, then you kind of are free to mix and match. They're kind of you can kind of permute them, right? There's other ways to get this, so I'll tell you a little bit about this maybe in Q&A. I initially wanted this to deal with lat long and geography. In 2010, there actually was relatively little of that on Twitter. If I were to do this now, there would probably be more of a location element to this model. So the sequence labeling factor is a straight up CRF. Almost nothing special about it. There's a lot of features for things like saying, is this token a user mention where the canonical name is inside of the biography of the mention. Standard features. This is a Wikipedia match for a band, a Wikipedia match for a place, word shape features, standard, everything you've seen a million times before. Term popularity is a little different. So what term popularity is doing is saying, if I tell you, for instance, that Dave Matthews in a particular message we believe is an artist, how does that align with the underlying canonical record? Okay, and so that is a factor which is basically finding the maximum alignment between tokens in the message of a given chunk with the underlying canonical field, and it has some IDF weighting because, so for instance, band is in a lot of things, and so that's less valuable than Dave or Matthews, for instance, right? So. Record uniqueness. So the kind of high-level goal of record uniqueness is to ensure that records are distinct from one another, because what tends to happen in these kind of models is if there's a very popular event, the model will expound many records to try to explain the same event on all the variations of the fields. And so what you want to do is say, no, I don't want you to learn two records that have similar field values. So for instance, it's bad to learn Yonder Mountain Band is playing and then Yonder Mountain is playing. Right? And depending on the frequency of the messages with those events, that's actually what will end up happening. Right? So my primary NLP background, so I did a lot of work in NLP across almost every major application, and most of it is unsupervised stuff. And so the kind of weird ways in which models pick up on different cues is a lot of what I guard against. And for what it's worth, factor graphs were I think the best way to do that. So record consistency. So this is the one I mentioned earlier about how nothing in the model is caring about permuting different fields across records. And so this will actually encourage you to have positive popularity with multiple labels in a given message. Right. So this is what stops the model from being symmetric with respect to different fields across different records. Okay. And I'll actually provide evaluation with and without this factor, because in some sense this factor makes your precision good, but your recall worse. So I'll talk a little bit about that. So the inference for this model is just standard mean fields, variational inference, nothing kind of special here. I don't like to try to do anything fancy with machine learning if I don't have to. So standard thing. You assume a variational distribution and that the posterior is independent amongst all the latent variables. Update each one independently. So experimental details. So for our data, we took gold concerts from nyc.com. So we just went to a website, scraped it, got all the different concerts happening in a weekend. There unfortunately weren't a lot of them. And in the paper, we go into some detail of analyzing records that we induced that weren't in this data. But for the purpose of evaluation, we're only reporting what there actually happened to have been a gold record for. So we trained on 1 weekend's worth of data, and then we tested on 2 separate weekends of data. And so for each weekend of concerts, we extracted tweets from that weekend that were in and around New York. And we built a classifier that detected whether or not it looked like people were actually trying to talk about going to a concert. Because most tweets obviously aren't about that, right? Most of you can probably tell me what tweets are mostly about, but it's not concerts. And so we built something that has high recall here for just picking out things that look like they're vaguely about concerts. Okay? So we did a couple baselines. String overlap with a given list of artists and venues from Wikipedia. There was this Mann-Urowski thing from 2005 where they basically had a CRF that was kind of trained for high recall, and they kind of had some heuristic way of picking out things that occurred in the same messages. And there's also just a CRF with a very low threshold. So I'll let you guys guess, which of these baselines do you think does best? It's a good test of how long you've been doing this stuff for. Wikipedia, yeah, of course, right? Like, this is one of these weird, disappointing things you learn. Of course, the Wikipedia one is best, other than ours, of course, because I wouldn't be giving you this talk. So the purple, so this is recall against the gold events. You must match every field in a record. So it's kind of the very tight, everything has to match. So the purple line is us. So the y-axis is recall, and the x-axis is the multiple of the gold records. So in other words, jumping over here. So if you force me to say you can only extract as many records as there actually are, our recall matches the best other baselines. You wouldn't actually do that in practice. You would actually say, okay, let me get 2, 3, 4, 5x what I think there is, and our recall kind of trumps over the list baseline, which is in green. And the other ones have trouble getting high recall. So kind of if you let me extract as many records as I want, the best recall I can get is about 12% absolute greater, or roughly 24% relative increase in recall. So remember that the recall is the same when k equals 1, i.e. you have the same number of gold records. Here's precision. So on precision, we kind of destroy everything else when we actually keep the records to a multiple of the real ones. So that purple line up there is ours. If you let us extract enough records, eventually our precision will drop down to everyone else's. So that blue line up there is actually our work plus the consistency thing. So plus that consistency factor. So that blue line is ours. That consistency thing gives you really high recall because it basically throws out everything which doesn't have a message which has multiple fields in it. Really high precision, terrible recall. So I didn't even put the recall up there because it's like less than 10%, I believe. Conclusions. So this is consensus information extraction over social media messages. We presented a factor graph model and some efficient variational inference algorithms. So I didn't talk about this, but the paper has some details about how you do this efficiently, because it's actually very easy to do it in a way that's completely intractable. And so you have to actually build real inverted indices, kind of like in search, to actually pull this off. And finally, I think there's a lot more interesting stuff to do here. So some of what I'm doing here is telling you about the things that I think are still worth exploring. And I still think there's a lot of interesting things to do here, especially with more specifically around space in the form of lat longs. And I can get into more details during a subsequent interview.
Quick question. So was time the date of the event, that was one of the fields, or?
So in the paper, we talk about it a little bit. We didn't have, there wasn't enough data with time, right? So people, yeah, so your expectation is that people talk about the event close to the real time of it. And so we talk a little bit about that. So that was something we tried. There just wasn't enough data to actually support it. So a big problem with this is 2010. It was still a little early, I think, for this. I think a lot more people are tweeting at concerts now in various ways, and this would, in some sense, be easier and harder, I guess. But
The reason I was asking that is I was thinking through, right, often people will say this thing is happening tomorrow, right, so it'll be a relative reference. And one of the interesting things, right, is if you take a word like tomorrow, it's amazing the myriad ways in which people spell a simple word like tomorrow, because it's Twitter, so you have TMRW and lots of ways. And actually, right, there's a lot of low-level phenomena that you didn't mention, like misspelling, like miscapitalization, et cetera, and those in turn break some of the standard features like part-of-speech tagging and so on. So I guess my question is, you talked at the higher level, but in terms of the low-level NLP, did you build your own?
So the similarity, so the similarity is IDF based and allows at a distance of 2. Yeah. So that factor, the nice thing about the factor is it lets you kind of do whatever, and so it was basically, you got an exact match weighted by IDF, and then you were allowed some edit distance from there. Now that wasn't enough edit distance. Like I think for Twitter and social media, edit distance is different. It's like drop vowels for free, truncate the end of a word if it's actually unique for free. So it's like whatever the entropy is of the prefix relative to the whole word. Stuff like, we didn't do some of that more fancier stuff, but I think even to get off the ground, spelling and handling at mentions and IDF weighting were kind of bare minimums for making it work. Yeah. Okay, content models for information extraction. So this is work done with Christy Sauper and Regina Barsley at MIT. So again, this was another social media example. So you can tell kind of at this point in my academic career, I was interested in kind of applications with real user data. The task here is to take a Yelp review and to extract kind of nuggets where people are expressing sentiment towards some aspect of a thing, right, of an entity. And so for Yelp, it's just poise or points of interest. And so for instance, you can talk about the atmosphere in a place being really awesome. You can talk about the food being great, the service being friendlier, and the impatient waiters. And so the crucial thing here is that this task is actually heavily influenced by context. So if I show you just this phrase, loved it, right? You don't know what they're talking about if you're just using kind of a 1-degree Markov model, right? Or if you have to use features arbitrarily back in the tokens to get this. But if you actually have kind of content structure overlaid on this, and you know that this is the paragraph or the sentence where they're talking about food, it's a lot easier to notice that, oh, that loved it must be in reference to the food. And so a lot of this work is motivated by kind of injecting that content model structure into kind of into an actual CRF so that it picks it, so it picks those up and it's allowed to use those to make judgments. Okay, so again, the disconnect here is between 2 different areas of NLP that I was aware of. So on the one hand, you have discourse modeling, which is a lot of the kind of stuff I did with co-reference resolution and topic modeling, which is understanding the bigger structure of a document or distributed discourse in the case of, say, Twitter, and then analysis applications, which are kind of part of speech tagging, anything which is using a CRF, like a lot of information extraction, I think looks, or at the time looked like that. So it was trying to do something that bridges these 2. And so the approach that we came up with is that we're still going to do an analysis application. They're still extracting significant chunks of localized phrases. And that looks like this, right? This looks like NER in some sense. It's basically take a phrase and not only highlight some phrase, but say what they're talking about, what aspect they're referring to. And the content structure, which is what rhetorically is the user trying to do in the review, that's latent, right? So that's not something you see. So when we label a document, we highlight phrases and we say that they're talking about food, they're talking about atmosphere. And then the content structure is latent because it's almost impossible to really annotate, especially since we did this on Mechanical Turk. It was particularly difficult to try to get someone to annotate that. And so what we're going to do is we're going to get a limited amount of the labeled data for individual phrases, and we're going to take a lot of reviews because that's an unsupervised model, just learning kind of the content structure of reviews. We're going to take tons and tons of reviews and hope that helps us actually do better on this kind of CRF model. Okay, so we're going to jointly learn structure. So structure means content models, and task parameters, like the actual specific tasks that you're doing. And the topics are latent variables that are going to be shaped by the underlying discriminative goal of the task. So this was kind of derived as a way to, at the time I was very interested in, because I'd done a lot of latent variable models, I was interested in latent variable models being used inside of towards a discriminative goal. I guess everyone trains deep nets now, and I guess that's more of a standard thing. But at the time, I don't think that there wasn't necessarily a lot of this going on. So the overall model summary is as follows. So this is kind of get into graphical model territory, but I'm going to use theta to refer to kind of content structure parameters. T is going to refer to the topical structure of a discourse or a document. The actual text is going to be composed of sentences. And then down at the bottom, you're going to have y, which is the actual thing that you're trying to do, and phi are going to be the parameters for that model. If you'll notice, my earlier arrows were directed because that was generative, and this arrow between s and y is actually undirected because it'll be a discriminative model or just a CRF particularly. And so this is actually the thing that you're trying to do. And crucially, we're going to add an undirected edge between the topical structure and the actual labels that you're trying to extract. So I'm pulling a huge cheat in this slide. I don't know if you can notice it, but I'm pretending like there's alignment between these colors and these colors, right? So I'm pretending like you're learning a food topic and you're knowing, oh, it's food, and so loved it means food. In reality, there's no connection. That is purely a rhetorical trick. The content structure does, in general, tend to overlap with task labels for this, but it's not necessarily the case. OK, so in particular, that blue content model, that's just a sentence level HMM, right? That's just, there's a topic in each sentence, there's an HMM, there's a HMM amongst them. Each sentence is dumping out a bag of words. That's it, really simple. The task is just a token level CRF. So again, this is identical to the sequence labeling part from the event discovery stuff.
Why did you use an HMM in the first case and not CRF for the other?
So this has to be trainable unlabeled. And this has to, and so my preference is to be discriminative, and CRF's better. They're hard to train unlabeled. Yeah. So this is what a CRF looks by itself. So if you do NER or some information extraction models, you have a document, but in reality, independent sentences are each their own CRF, and you kind of train a model on all of them. Okay. And so we're going to augment this with kind of topical structure from the actual document. Right. So here, this looks like a standard CRF model. And now what we're going to do is each sentence is going to have these kind of HMM topics kind of floating throughout them. And then crucially, we're going to have features between the topical structure and the actual CRF. So I'm going to explode this out a little bit. So each topic is going to emit a bunch of words, and then strictly speaking, I don't know how much you want to delve into this. CRFs are basically, in some sense, from a discriminative point of view, it's just this is really the CRF, and you're allowed to freely condition on all the observed stuff, not just, it's not an HMM, right? It really looks like this, and this is all a big observed clique, right? This is a mistake I often see students make with CRFs, but you're freely allowed to condition all the observable stuff, and so basically this is hooked up to this big clique right here, and this edge is going to be things like, does my corresponding word is loved, and my corresponding word is loved, and the identity of the second topic is the quote unquote food one, right? And so implicitly the CRF will learn the correlation between the topic latent variable identity and its task parameter.
Do you assume you get a unique topic for each sentence?
Huh?
Does each sentence have only one topic?
Yeah. I mean, that's all changeable. My kind of bias, I guess as an academic, the way that you think about this is more, what is the unique kind of narrative of this, and what's the simplest instantiation of it? And the simplest instantiation is kind of just a sentence level HMM. Okay, so I'm going to probably blaze through this a little bit more. If you're wondering how you actually learn something like this, it's actually totally well founded. You just have a bunch of topic variables, words, and y, and then you basically factorize this, and it ends up looking like, so if you kind of group together the CRF component with the bag of words emission, this actually is just an HMM with an observation of both the sentence and the task label on the label data. Yeah.
Sorry, I might have missed something, but the set of topics, it's a finite discrete set.
Yep.
And it's pre-chosen?
It's the numbers chosen. So the only thing is the number is chosen, and then they're commutable after that, right? So in particular, this content model is the Barzilai and Lee from 2004 paper on document structure analysis or whatever. So this is a standard model for doing document structure analysis. This is why it was used also. Yep. So kind of if you rearrange terms, this actually is just a big HMM that happens to have this discriminative term in there. This is kind of a neat trick. And then the way that you actually learn this model is, again, you maximize your observed data for labeled data is the sentences and the CRF labels, the task labels. And then you marginalize that out T, and then you end up with just a normal EM objective. So your E step can be computed by running forward backwards as normal with an HMM, except that you also add a term for kind of the probability of Y star, which is actually what you get when you, this is actually log Z for the CRF, without delving into too much details here. But it's basically a term that you compute anyway when you train a CRF model. And so basically you run the CRF, and as a result of computing the CRF, you actually compute this, and then you take all those values and you throw them into kind of a forwards-backward computation to actually do your E step. And again, the only latent variable at training time is T, the topics. Okay, so this is standard. So the M step is actually identical to everything you've seen before. The tricky thing, the M step for the content parameters is basically just the M step of normal HMM. So you collected a bunch of counts, you normalize the probability of a word given a topic. That's all normal. It's trickier here for the CRF model, right? Because now the CRF model ends up having to do something that's actually non-convex, so a weighted conditional likelihood objective. So if you didn't observe T and you just drop these two, that would be normal CRF training, right? So that would be normal CRF training. When you have a latent variable, you have to actually perform this expectation calculation here. Now the interesting thing is, because this is only once per sentence, you can actually just explicitly, it's one of these few times where you don't have to do anything clever. You can actually just enumerate out the different, basically you run the CRF for each topic. So if you have 10 topics, you run the CRF. When you do your maximization, you basically get 10 CRF inputs, one where a topic is fixed for each one, and then you just train normally. Okay. So those details are a little, so the only takeaway here, because I don't expect people to follow this much math this quickly, is basically it looks like the EM algorithm, and there's a small variation on both the content model stuff and the CRF stuff. So what I've told you so far is about labeled data, but the whole point of this was actually that you get to use a bunch of unlabeled data, right? And so what will happen is you'll get some labeled data, right? And then you'll also get just a ton of unlabeled data. And the unlabeled data obviously isn't going to use the task parameters, right? So it's obviously not going to use any of the CRF stuff. It's only going to be training the content model parameters. That's all you're going to do. And so interestingly enough, some people, I've heard people ask me, well, what happens to Y here? And it turns out that if you don't observe the task labels and you just marginalize over them, and you treat them as latent variables on the unlabeled data, it comes out to just that anyway, right? Because the task Ys are just at the bottom. They're the leaves of a graphical model, and so they just marginalize out, right? So you end up with something sane, right? And so you end up with this objective. So basically, when you do an EM algorithm, you kind of do a loop over your labeled data, and then you do much more over the unlabeled data. Experiments. Okay, so there's two domains here. One of them is Amazon TV reviews. So this is people talking about the crispness of the picture, how easy the remote control is to use, how good is the actual TV like itself, how good is the software on the TV, a couple different aspects, things like that. And so you got a bunch of training and test documents, but in reality, documents aren't the thing you train and test on. It's individual tokens because it's a CRF. And there's roughly 12.6 thousand unlabeled documents. So this was meant to be like a light supervised thing, like label as little data as possible, or not as little, but a smallish amount of data, and use a bunch of unlabeled data. And we also did Yelp reviews as well. And we scraped a bunch of Yelp reviews out. Okay. So the results here are token F, the aggregate token F measure over the non-background stuff. So just like when you do NER, you report F measure on all the labels except the none label, right? Just when you do normal NER evaluation, this is the same thing. So there's 3 models we'll compare. One of them is just using a CRF, so screw this whole unsupervised topic model stuff, just train this thing. There's the independent content model, which is basically train the content model parameters separately, like train an HMM, and then just use that and train the CRF separately, right? So this is kind of like what like all those early DeepNet papers that basically were like, oh, just do a bunch of stuff unsupervised and then plug those in as features, more or less. And then there's joint content model, so that doing both at the same time. Okay, so kind of this is roughly the curve you'd expect. You get fairly significant gains in F1 measure on the Amazon task as you inject a content model and then finally you train them jointly. The truth is, in terms of, every time you make a decision about, it's interesting because like I look at this very differently as someone who's not primarily an academic now. This is the benefit is the distance between those bars, but the other unstated part is complexity. And so, to be perfectly honest, the green bar maximizes quality and complexity. Yeah.
The other question I have is with the green bar, if you're doing it independently, can't you use possibly more complex content models than?
You could use You could use more complex content models regardless. Yeah, you could, if you wanted to do something sub-sentence and sample, like if you wanted to actually have like some kind of hierarchical LDA instead, you could do that.
So there's no inferential problem.
There's nothing stopping you other than maybe it just becomes, there's more time because but there's nothing that complicated. It's all tractable. Again, like I was not trying to do anything complicated with either of these things in terms of, because when you do something complicated that conjoins 2 things, you want to make each thing simplest as possible. I imagine it might help. To be honest, I don't know if it would even help. Like I'm not sure it would help because if you actually look at some of those documents for what you're actually doing for, say, the Amazon reviews, people are talking about, some aspect of the product, and then it's not like actual sentiment analysis. There's actually a sentiment analysis experiment in the paper that I'm not doing in this talk, which is more, which delves into more of that kind of stuff. But yeah. So that's Amazon, and here's Yelp. So again, for both bars, to be perfectly honest, the green one is sane. You get some gains out of the joint stuff, but I call that an academic gain mostly, to be perfectly honest. It's possible and doable, but there it is. Okay, so conclusions. So modeling content structure improves text analysis applications. Cleverly worded to be ambiguous about whether or not you need to do them together or separately, but there you go. So shaping content models to specific tasks is beneficial, and I bet that you could find if you were trying to actually prove that you wanted to do them jointly, I'm sure you could find domains and models where that was the case. For these 2 particular ones, there was a gain, but it's not a lot. So unlabeled data yields further improvements. This is actually true regardless. So in the paper, I have some charts about how much unlabeled data you use, either independently or in the joint, and that is actually beneficial. Okay, so now I'm going to totally shift gears, and I'm going to talk about relevance engineering. So this is work I did while I was at Prismatic with the entire Prismatic backend team, which at the time was Jenny Finkel, Jason Wolf, David Golan, and Ian Wong. Okay, so this was a talk that actually Jenny initially gave at Strange Loop that we did together, and I've done this talk in a few other places. So if you like this, there's actually a video of me on my website doing the full hour-and-a-half long version of this. This is kind of a excerpted version of this. Cliff Notes, right. So back in 2011, I started this company called Prismatic that was meant to do content discovery. So learning about a person and what they cared about, and then finding them content that matched that. There's a lot of kind of NLP in machine learning here when it came to text analysis and document analysis. I'm actually not going to talk about that. I'm going to talk about the personalization aspect of it because I think that's where the learning a topic model in a company is not that different than the offline. Is not that different than kind of the academic stuff. It's the personalization, because that's more tied to kind of product and business goals, becomes a little more interesting, and I'll talk some about that. So the company was meant to do content discovery, and in particular kind of news article discovery. So someone would come in, we would learn a lot about them from Twitter, social networks, Facebook, et cetera, and the articles would have information about topics and publishers and actual text analysis, and the most important thing, more important than all of those, is actual behavior of users on the site with respect to articles. So that was actually the most dominant thing. So all of the kind of social network stuff was mostly to bootstrap people in, but once you actually have information on people and their behavior with content, it's actually more valuable than anything else. So the goal was to build a ranker to find a small number of great articles for a user from a large document index. So kind of at any time we had a few million-ish articles that we were considering for a person. A user comes in and we were doing kind of real-time personalization. So there was machine learning executing on an API call as soon as the user came in. Now it was just inference, so it was basically a bunch of dot products. Turns out that is even hard to do. And I'll get into, the most interesting part of this is some trick about how to do linear model inference for personalization that I'll talk about here. But so this was the goal. And so a good question to ask yourself is, how do you know you're doing a good job, right? Which is a hard question. And I think when I started the company, and I'd never even really written code that hit the internet that much, I would have said, oh, well, we're going to make an offline measure, and we're going to maximize the P at 1, and blah, 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 blah. And it turns out, no, it's improving user engagement, right? So the bottom line of this is how do you improve is really a metric that is quantifiable and trackable, which is how do you improve user engagement? In particular, if any of you have consumer startup experience, a lot of people measure D6 and D7. So how many weekly actives show up 6 or 7 days a week, right, as a percentage of your weekly actives. And so ultimately, what we wanted to show is that we wanted to know that there was some offline metric that we could optimize that was correlated with improved user engagement. So you can't really train a relevance model on user engagement, right? Because user engagement is what does a user do the week after they first show up? Did they churn? How many days did they show up this week? It's not localized to any article choice, right? Machine learning is all about like decisions localized to a specific context.
Why can't you just train based on actual engaging actions?
You can, but how do you know that's correlated with user engagement?
It is user engagement, right? That's
No. User engagement is no. You're thinking like an engineer. Like I'm thinking like no one comes and says how many articles. They're actually like how many people showed up and stayed next week. If you're Netflix, right? You make a recommendation, and a user may watch that, but that's not the thing that they care about. They care about after your first free month, did you keep subscribing? That's the thing you care about. Right. And so it's actually really, and even for Netflix, I think they have a hard time establishing correlation between kind of research metrics and business metrics, right? So this is actually easier for us. So we actually can just run a simple linear regression model on, how many days a week will this user show up, given their article interactions on the first day. And there is actually correlation there, right? So it's interesting because it's not quite the thing you'd expect, because it's for instance. Things like dwell are more correlated with user engagement, for us at least, are more correlated with user engagement than, say, a user shared an article, right?
So is the issue here one of data volume and time scale? In other words, if I told you, hey, I've got 10 million users and 5 years of data, would the issue you're talking about go away?
No, I think it's more about in other words, it's like, what counts as the positive signal? Is it when you just read an article and click on it? Do you have to dwell on it? Do you have to share it?
No, I get that. So clearly from the business point of view, what counts as a positive signal is something that correlates very directly with revenue.
Yeah.
But it seems like you can just label your examples based on that.
Right.
And you're good,
right,
if you have enough data.
Yeah, so I think there's always positive correlation. I think the place where you get into trouble is that there's so many other confounding variables that the correlation is really hard to identify. It's like the site was too slow. Right, because an input to your model should probably be what was their initial latency, things like that. Like what time of day do they should? There's a lot of confounding variables. So you're right that a lot of data would help, but it's almost impossible to get enough data to kind of suss that noise out. Yeah.
But at Bing, we had the same issue.
Yeah.
We still do machine learning, so we track user engagement separately from the things that you can learn.
Yep.
So
did we. The issue for us was justifying time spent on. We were a small team, and so it was more about like, it was the same people building the iPhone app that were building the backend, and so it was like, if we have to move the needle here, are we going to move it on the machine learning side of thing? Is that where there's upward mobility? When you're in a bigger company, it's kind of easier because you just have a team dedicated to that anyway. It may be hard to tell like how much you can actually invest in that area to make things better, but anyway, so. So we ended up doing kind of what you guys suggested, which is, there's machine learning on the offline metrics, but we spent a lot of time making sure that that actually made sense, because it's not actually immediately clear. And in some cases, I've talked to some folks and consulted with some folks where there's actually no relationship between the research problem and the business metrics, which is not a great place to be in if you like research. So we save all the session information, and we're primarily going to train models on user-article interactions, right? And so we save everything, obviously. Positive examples are users clicking, sharing. We don't mention it, but dwelling and saving an article. And they're weighted differently. That's the prudent thing. So the weight of those things is determined by kind of how well they correlate with downstream user engagement. And there's some negative examples. So users Xing out an article. Scrolling past an article is kind of a negative signal at a certain amount of time. It's a weak negative example. And so this part of the talk is stuff that you guys will all be familiar with. There's a simple linear model that has features between a user and an article. So does the article follow a topic on this document? How many times has the user previously clicked on this publisher before? How many times has the user removed this publisher? Does the article have a picture? The number of other prismatic users who have liked the article, et cetera, et cetera. And so you have feature values for all these things. You train some model that I'll talk about in a sec, and you get weights for them, and then bada bing, bada boom, you get a dot product, and that's an indication of the user article affinity. Simple linear model. It's actually just a simple logistic regression model. We tried more complicated things. Turns out not to matter that much, which is kind of a good lesson, right? I mean, when we started with logistic regression, and we thought we talked to them and tried more. They're more complicated things, but none of them actually provide enough of a lift to actually necessarily be worthwhile.
How many features do you have?
It's a little tricky. It was on the order of 10, 15,000. Because there were features on individual. It gets a little tricky for a reason I'll get to in a second, but it's about 10 to 15,000 depending on how you counted. And we tried more features too, right? We tried like hundreds of thousands, because I come from NLP, right? I'm used to like hundreds of thousands of features. There was a trade-off there between inference time. Because remember, this is not asynchronous, right? This is not train the model offline and present the recommendations to user when they log in. This is real time. And so every feature has a cost associated with it.
Okay, I think what you say should be in the first page of every textbook.
Yeah.
Try a linear model and don't venture anywhere else.
Yeah.
I think that should be the first page.
So at the fruit company, I've seen, like, I think a lot of it is whether you're online or offline or how much explication you need in your model. Like I don't, my view is a little nuanced. I always tell people to start with the simplest thing, and if the simplest thing doesn't work, then it's unlikely. I've never seen a case where like a nonlinear model is going to get a positive output, give you a positive output, but a linear model won't. And so it's usually like incremental stuff. And so you might as well try the simple thing to discard a hypothesis, because a lot of things aren't learnable from user data, right? I mean, I could have done a whole talk about all the things that aren't learnable or not easily learnable. There's too much noise. Okay, and so here, normal thing happens when we train. We take a session log. We know we can predict the infinity here. And there's times in your training data where your stored session has a different article ranking than what you presented to the user that presumably is more positive. And the next time you do the session, you sort by those scores. And so the classification is really straightforward. It's just use the learned weight to score articles, sort articles by score. There's some diversification component that I won't get into right now, but it's pretty standard if you follow actually search-like stuff. And the problem is the simple classification process is just way too slow, way too slow to actually be usable. And so, and the issue is that you can't actually do real-time personalization if you have to construct a feature vector for every new user article pair. Because at runtime, we're approximately doing 10,000 dot products, right? And that's just not possible. So we did this little trick. So this is the way you think about this if you think about this as a research problem. So there's a universal weight vector on some of this stuff, and the features are user-specific. How often did this user click on something? How often did this user click on this publisher? How many prismatic users like this user clicked on this publisher, et cetera, et cetera. Okay, and so basically, if you think of things that way, you construct feature vectors per user article pair, which is impossible. So what we did instead was this. We did this trick that I need probably a whiteboard to explain a little better, and is the weight vector is actually user-specific, but the features are universal. So in particular, if you assume if you assume that all of your user-specific features can be projected to basic article features, then you can do this trick where instead of actually putting that weight there, you can actually just move it. You can actually just to the feature, but you can actually just move it to the weight vector. So this is a particular assumption. So in other words, the specific assumption is every user-specific feature is a linear combination of article features. So this is really so if I were to do math, it was the feature vector for a user and an article can be decomposed or factorized into a feature vector for the article plus some linear combination of user-specific stuff. And then if you do this, then you have no object construction at runtime.
Does that explode your feature space?
No, it's the opposite. It keeps your feature space small. You can't do, for example, we can't do what is the max number of clicks of any of the topics on this article that the user tapped before. We can't do that because that's not a linear combination we can't express that feature. So I've actually never seen, what's interesting is, if you've done machine learning in practice, feature engineering is really, really important, despite what the deep net people say. It's really, really important. There's very few people who study kind of properties of what's expressible as a feature or any of the software engineering about feature engineering, and I'll talk about that in a sec, because there's a lot of issues you get into, but what this is basically saying is it's a constraint on your ability to do feature engineering that yields a very efficient formulation where you do no feature vector construction. And I haven't seen anyone talk about this before. I've mentioned this to a few people, and they're like, oh yeah, that's interesting, but no one really thinks about kind of the theoretical properties of feature engineering, because it seems like such a kind of applied thing. Yeah?
So we were talking about everything was too slow. It was because the feature extraction was too slow, not the classification.
Yeah, so our feature extraction was tuned, so that was the first order thing, but that you can tune. You can make your feature extraction faster. If you're still real time making objects for each user article pair, you're going to hit some baseline that's a lot harder to optimize around, which is like you have to actually, especially since the feature vectors can be different sizes for everything. Yeah.
The point that you're just making, is it have anything to do with the same thing as like the decomposability of certain features in terms of like a structured model? Like, for instance, in parsing, for instance, you can use a max feature because of the fact that you have to be able to decompose it.
It's related, but it's definitely related. So it's an assumption of linearity. But so typically when you make the linearity assumptions, it's on model structure. This is not that. The model's still simple and linear. It's on the structure of the features, which is a thing you never hear people really talk about. Like, you can do this with other things too, right? Like if you have a feature this is another useful trick. How often do you have a feature which is the conjunct of two other features? Pretty often. So you can actually push around your weight vector so that you actually get a sane behavior if you're willing to do certain tricks with your feature vectors too, right? So that's another thing, right? If you use a lot of conjunctions of features, you can do these other tricks to make stuff faster, which is actually important for real-time stuff. Like, again, if we were doing offline, if we were like make articles and do recommendations and serve it up to a user with like an hour latency, I probably wouldn't have done any of this. It's only because like it's real time that I think it matters. Yeah.
So when you say optimization due to the cost of object construction, what do you mean by object construction?
We were using Java. I mean, it was Clojure, but this was done in Java because like all the heavy lifting, unfortunately, was in Java.
Because in this kind of synchronous, super low latency environment that I've seen before, everything is just a giant blob of memory. Yeah. You don't do any kind of memory.
But we did.
Object.
Right. So in particular, right. So that's what we got here. So the feature vectors on the articles were static, and we only made one vector for the user. And then that's how because you're right, when you do like low latency stuff, you can't create objects like that. That's crazy.
What I've seen is you have a giant memory block
that
has everything, and you just reference that.
The problem is you have to do some computation because it's user specific. So depending on the user request, you get very different things. Yeah.
It seems like you still have to, are you really not making any big objects? Because it seems like you've got the feature vector for the user, you've got the feature vector.
The weight vector for the user.
Sure.
That's made once.
Right, and then you've got the one for each of the documents.
Which is fixed, static.
Right.
Yeah.
Now you have their interaction, which is...
No, it's just the dot product. That's the whole point. It's just a simple dot product.
Okay, so you actually explode out the cross product that was originally on both of them into both their...
Exactly. So I pay the upfront cost instead of paying it exactly. So my feature vector for the document is bigger than it might otherwise be because it has all these linear combinations of things from the user, for, like potentially the user could care about. But that's done once per document. Yeah. So that's the trick. Okay, so I'm going to briefly go through some challenges that we face. Checking on time here.
I mean, it seems like you've lost some expressivity.
Yep. You have.
And that hurts the performance?
It doesn't hurt when you say perform. So quality, yeah. so I was a CTO, so I thought about both. So So you can do offline. In particular, our offline experiments still look like the original formulation. It's only when we have this online path that you do that. So we can tell how much the offline metric moves. We can't tell how much the online metric moves because that's too slow. But we can tell how much the offline did. And yeah, we were sacrificing stuff. But like if the option was that or like several seconds in kind of the global optimization, it wasn't probably worth it. So data bugs are the worst. I want to talk about data bugs because every time I've ever consulted for people who do machine learning in the past and stuff hasn't worked, it's actually just been because they've had a bug and not known it and kind of dismissed all of machine learning in the process. And so I want to talk a little bit about it because it's very easy to get into data bugs. In particular, how many people are aware of the time traveling bug? Time traveling when you do any kind of ranking, if you're Netflix or a search engine or something. I'll talk a little about the time traveling bug. So researchers will get all excited, they'll get some offline data and they'll get some big offline improvements and they'll be really happy. And then you actually go to do an A/B experiment with your model and it's terrible. The online performance looks nothing like, and when I say online, I mean in production, not like online or versus batch machine learning. It's terrible. That happens. I've seen that happen all the time. It's happened to me at Fruit Company. It's happened to me at Prismatic. I've seen in consults for other people for whom it's happened. And oftentimes, people typically just give up. But if you're tenacious and have a bunch of people who give a shit, you're going to actually dig into it. And there's interesting things that actually happen, and there's systematic reasons why you get this kind of stuff. So I'll give you an example. This is an instance of the time traveling bug. So the time traveling bug is if you tend to have a lot of features during training time. The feature value, you have a feature which is related to time, and you incorrectly snapshotted the user data you've incorrectly done a user snapshot. This happens all the time and people don't even think about it or notice it, especially when you have arbitrary feature functions. So during training, you have a feature on how often a user has clicked on a publisher before, right? And so what should happen is during training, the feature value for every article where the user's never seen that publisher before should be 0. However, if the way in which you snapshot that data comes after the time at which you've trained, it's going to be positive for the times in the session where the user actually did it. And so you never actually see a place where that feature value is 0. It's instead always greater than 0. And so you basically learn the wrong thing. The optimization ruthlessly exploits this bug, and it makes you look like you're doing really awesome because in some sense it's a real cheating feature. Right? It's a cheating feature because you've peered into the future. This is really easy to do the more kind of resources and things that you use. So as a first order principle, so we saw this, and as a first order principle, being able to replay sessions exactly and have everything be time ranged is crucial. This is a systems engineering problem that you run into as soon as you do machine learning data. It's really crucial and it's very easy to screw up. So Netflix, for the longest time, I talked to some people at Netflix, and for the longest time they actually had similar bugs like this where they somehow it leaks in through a feature. And it's not always in some way this obvious, but there are other ways in which you can leak information from the future.
But the linear model will be very robust against this kind of thing.
No, it's not. You have a feature which basically encodes the user actually touched this article. Because publishers are a very sparse feature. Linear and sparsity aren't the same thing. It affects a sparse feature more. So if you have a feature on an individual publisher identity, and those are almost always really sparse, it's basically a cheating feature because it's telling you, oh, the users clicked on this in the past. Or the users clicked on this, and you learn that you get a very high weight there.
Wouldn't regularization help with this?
It can, but it's still going to give it a very small positive weight. So you're still going to regularize, but you're still cheating, right? You're still going to get a better result offline than you do online. Regularization helps. Yeah, if you didn't regularize, you get 100%, right?
So 2-3 minutes.
Oh yeah, okay. Ranking versus normal machine learning. So interesting things happen. So when you train a model, and you have a negative feature, you tend to and you deploy that model to production. You tend to compensate, and you say, oh, I don't show many of these articles, but when I do, they're good. And then it turns out you kind of go the other direction. You go, oh yeah, I love this thing, and so you bounce back and forth if you have a discrete feature on a publisher. So the answer is don't have a discrete feature on a publisher. Have features which are always self-regulating. So meaning the feature is what is the percentage of taps on this article publisher given the number of views. And that's self-regulating. Discrete features are not self-regulating. They have this tendency to bounce back and forth if you do discrete deploys. Last one I'll talk about that's really interesting, and then I'll end, statistical bleeding. So this is how A/B tests can influence each other. So we ran an A/B test between, we typically used to have 8 systems in production. We ran an A/B test with 2 different types of systems. One was called the Explorer and one was called the Exploiter. So a brand new article would enter the index and the Explorer would show it to an article who then clicks on it. So the Explorer was willing to try totally crazy articles, and sometimes it would win, right? And so then the statistics on that article get updated, because like I said, there's a lot of statistics about user interaction. And then the exploiter sees which articles win, and then it starts showing it to people, right? What happens in an A/B experiment is you're like, the exploiter's doing really well. And then you start to ramp up the allocation of the explorer and ramp down the exploiter, or you ramp up the exploiter and you ramp down the explorer, and then it gets worse, right? Because A/B tests are never independent. Right, like that.
A credit assignment problem, right? If
Yeah.
you treated Morse reinforcement learning or something, you would
That's right.
do it.
So the big lesson is, as we went in Prismatic, things looked more and more like reinforcement learning, and at some point things got more and more like that. And yeah.
So why can't you avoid this if you just make sure that not only are you A/B testing on the users, but you're A/B testing on the data?
Mm-hmm.
You're actually only letting the exploration go over certain data that is not actually going to be shown in the set.
We ended up doing something like that. At some point, if you fork all of the statistics according to A/B experiments, you end up in kind of a certain kind of hell that you don't want to be in. Because if you think about it, like you're basically all of the resources which are conditionally influencing the features have to be forked by A/B experiment, which becomes a little hard. Because then it's really hard to introduce a 1% experiment if you rely on statistics. So there's ways around this that I won't talk about now. But that's basically it. The results were, when we went from a trained model to a non-trained model, we had much more shares, much more likely that the first stock P at 1 was good, 14% longer sessions, 15% fewer crap sessions, and actually user engagement increases as well. Okay, that's it. Did I finish in time? Thanks.